Hello everybody, we're UAV Forge. My name is Christopher Pridgick. I'm the Chief Engineer and Controls Team Lead.
I'm Jose Ortega. I'm the Project Manager and Fabrication Lead.
I'm Anna Isaacson. I'm the Software Team Lead and the ICS Correspondent.
And we're going to be telling you guys today how we're inspiring innovation for personal autonomous systems here at UCI. So just to give you a quick overview of what we'll be covering, we'll talk about the history of the project and then start talking about the project specification and what our goals are. And then we'll start talking about our solution, both in software, hardware, and fabrication. And lastly, we'll finish off with our future plans and what we're missing.
So UAV Forge is a competition put out by DARPA 3 years ago that required to build an aircraft that can stream 3 hours of video for a 5-hour mission and it can fit in a backpack among many specifications. The designs were, from simple regular plane to regular quadcopters to a little more complex combination of both. But no one was able to complete every single specification that DARPA set out, so they closed the competition. Last year, some students decided to come together and try to attempt this again. We cut back on some of the specifications, like the 5-hour flight time, because that's not feasible right now. So our overall goal is to complete most of these from year to year until eventually we get this project down. Last year, it started off as a 20-person project for mechanical and aerospace engineers, but this year it expanded to much more to go in between schools. So now we're mechanical, aerospace, electrical, software, computer science. We've become much more in which our overall goal is to build a vertical takeoff system that also has forward flight capabilities and can be autonomous to where the user tells the aircraft where to go and it'll do it on its own, while avoiding obstacles.
Since last quarter, our project has grown quite a bit, and currently we have over 60 students in our project. To manage communication, we have set up a hierarchy system, and on the top of which are our chief engineer and our project manager. They're handling the administrative issues and also design decisions. We have currently 5 teams, and each team has a project. Each team has a team lead, which communicates project members to the project administration.
And with a project like this, there were a lot of needs and requirements, and a lot of these came from the competition that came out with DARPA. This is just a small picture of what we have so far. These tables are much bigger, but they wouldn't fit on the slides. But just to give an idea, like Jose said, we had things like the 4-mile round trip or the 5-hour mission time. Those were very concrete things that we need to meet. There's also things like it needs to be easy for a soldier to carry and light enough for a soldier to carry. And those are things that you really can't define with those terms. You need something that we can measure and test ourselves against. And so we then decided to limit sort of some of the geometric constraints on the airframe and started defining some goals we can reach on these sensors. So instead of saying, hey, our system's flexible, we can say, hey, our system meets these requirements and these specifications. And they all have very concrete values that we can measure and check back with our specification. All the teams are also able to check this specification and document their work on Google Drive. We have a folder system for that. And we also have Trello, which we use for communicating goals and tasks between people, teams, and the entire project.
So for the project design review, our goal is to have an autonomous quadcopter and a software system. So imagine we have a ground station over here, and then we have our UAV. I'll be able to go onto a ground station, enter some information about the project, like some waypoints and some other information. By hitting execute, this data will be packaged up and sent to the UAV. From that point on, the UAV will be able to take off autonomously, navigate itself through the environment using some obstacle avoidance algorithms, and land at the destination. For the software team, we have a ground station which enables the user to enter some information about the mission, store all this data, execute it by sending it to the UAV, and also it allows us to stream video directly from the UAV to the ground station. for the CV and AI, which is computer vision, artificial intelligence, our team is working on an obstacle avoidance algorithm that allows the UAV to go from point A to point B, avoiding obstacles.
So for fabrication, last year we built a quadcopter. Last quarter we built a regular RC plane. And right now we're trying to mesh these two together. So our current goal is to build a tilt rotor system, vertical takeoff forward flight, and we're accomplishing this using a tilt rotor mechanism that I designed. So it involves using planetary gears, and they servo connected to one of these gears to turn the overall system. And we're trying to keep this as light as possible, so we're using micro servos and we're playing with gear ratios to get enough torque to turn our overall system. So our current platforms are used for testing. We have a plane that we try to fly as much as we can. Right now we're stuck on fixed flight, so we have 2 motors on the end of our plane up there, and we're going to do a fixed flight to see how our plane can react to 2 motors and a pilot controlling it. And we have our quadcopter, which the software team uses to test cameras and LiDARs and other electronics.
And lastly, we have our hardware solution. So this boils down to what the CVAI team's doing hardware-wise. We have an embedded systems team, which focuses on taking what the CVAI team gets working on their laptop, and they translate that to run on embedded devices, as well as our control systems team writing low-level control for our platforms. And so this boils down to our flight control unit, which runs the control system at a high frequency and works between the artificial intelligence unit and the output to the motors to control the system. We have our embedded boards, which runs processing for the sensors and AI. And these boards vary in size, from the size of a quarter up to the size of about a credit card. We have our LiDAR sensor, which gives us a 320-degree view over 20 meters away from the UAV. And this runs at 40 hertz over an Ethernet, so we get a lot of data and a lot of information about our environment from that sensor. We also have a stereo camera rig, which is 2 cameras pointing in the same direction, a distance apart. And this allows us to gather depth, color, and object information. And if one of these camera fails, the nice thing is our system's redundant, and so we can stick with using one camera and gather depth information, doing those calculations on the ground station, and then send that data back to the UAV. And what's really cool about this, these are some qualitative goals that DARPA put out that they wanted the system to be, and this definitely makes the system informative, efficient, and flexible for the missions that we'll be performing. Now, some future plans. This project, again, stemmed from DARPA, and the big thing there was they had all these people from around the world bringing out ideas and projects they were working on. And so there's many ways to solve this problem, as we saw many of them from the project, and we're not necessarily saying the one we're doing now is the absolute best. But from our research, it looked like the best path to take right now. In the future, we could be working with swarming. We could be working with a tandem wing. We could be working with tilt rotors like we are now, or with some combination of both, a quad tilt rotor that Zero is putting together. But also the other thing is we got the guy here in the field doing actual testing like a soldier would. And that's something else that we're looking forward to do by the end of this year, is have a ruggedized platform, and we can then go out and test a few times without touching it or trying to fix it, to see if it's something that would also work out in the field.
So for cost, since we are a fairly new project, the bulk of our materials, or bulk of our costs do come from hardware. So buying tools that we need. We are fortunate enough to share a building with Human-Powered Airplane and Design Build Fly. So we do use their tools when we can, but we're trying to build our own library of tools so that we can, have our own work area to where we can build a plane from, beginning to end without any need for help. For other costs, other materials are, carbon fiber rods, foam, fiberglass, things to build our current platforms on, and that's just on the fabrication side. Other costs do include the electronics, and the bulk of our cost does come from trying to get an affordable LiDAR, which we have 2 right now because companies were gracious enough to donate them to us, but it is something that we do need to buy our own of. So our current cost right now is around $8,000, and that is because of the LiDAR is incorporating more than half of that cost.
So our project is different from any other senior engineering projects because it covers not only opportunities for students, but also opportunities for industries. This project bridges over not only departments that are in the engineering, but also over schools. And we provide a playground of knowledge for all the students that want to work on this project and develop what they want to develop and grow.
So our students build what they want to build. We do have an overall end goal, but how we go about that is what we want to build. We don't force students to, have a certain task completed a certain way. We encourage them to build what they want to build. And because of that, we're open to multiple disciplines. Like we had some students come up to us and say, hey, we want to build a website. So we have a website team building stuff and recording and documenting our information.
And lastly, this allows students really to build success here at UCI. And that's something that's very important because the success they have here, they'll carry on with themselves in the industry afterwards. And so that's really where we get a lot of experience. We get some sponsorship from companies. And it's been great to actually share ideas back and forth, gain advice from them, as well as the data and work we do applies to some of the stuff they do as well. And so it's very cool to get that interaction there between industry and the students here, allowing our project to succeed, as well as allowing them to bring stuff new to industry as well. And with that, I believe that ends our presentation. Are there any questions?